Okay, next we're going to look at what happens in the nucleus whenever it emits these types of radiation. So the first thing we'll look at is alpha. So here we have an alpha emitter. So we see the nucleus up here. The, everything we talk about here is nuclear radiation. In fact, we're not interested in the atom. We're just interested in the nucleus because that's where the radiation comes from. So this isotope of uranium, uranium-238, is an alpha emitter. So if we look at this nucleus, the bottom number tells us the number of protons. If we subtract the atomic number from the mass number, it gives us the number of neutrons. So if we do that, we get 146. So this nucleus here has 92 protons and 146 neutrons, but it's an alpha emitter. So this is eventually going to emit an alpha particle. Now our alpha particle here contains 2 protons and 2 neutrons. Now the effect of that is when the alpha particle leaves, it takes 2 of these protons with it, which means what's left behind won't have 92 protons anymore, it will have 90. And it takes 2 neutrons away. So rather than having 146, it'll have 144. So by ejecting the alpha particle, the nucleus itself changes, and therefore what's left behind will be a smaller nucleus. It will only have an atomic number of 90. If we add these two numbers together then to get the mass number, which is the number of protons and neutrons combined, its mass number will have changed into 2, 3, 4. Now that means it's not uranium anymore, because uranium always has an atomic number of 92. Now you won't be asked to learn off the periodic table or consult it. Sometimes the physicists would just say X because it's changed into some element we don't know. But in fact, if we do look up the periodic table, we find that uranium changes into thorium whenever it emits this alpha particle. And what we could do is we can represent that by an equation. These are called decay equations. And if we look up here, you can see it's just what we say there. We start off with uranium, atomic number of 92, mass number of 238. That changes into thorium with an atomic number of 90 and a mass number of 234, and an alpha particle, okay, which, because it contains 2 protons, has an atomic number of 2, and it also contains 2 neutrons, which means its overall mass number is 4. What you can be asked to do is to fill in the blanks. So for instance, let's say you were not given this number and you maybe weren't given this number, okay? All you have to do for these is make sure they add up across the equal sign. So if we do the top line, 238 equals something plus 4, that must be 234. The bottom line, 90 plus 2 on the right hand side means we need 92 over there, okay? So the equation balances the masses, the mass numbers and the atomic numbers must add up either side of the equal sign. And it makes sense because we remove 4 of these, so this will drop down to 2, 3, 4. Meanwhile, we remove 2 of those, 2 protons, so the atomic number will drop down by 2.